Gents, here's part two, or homework part two for series two for the test that's going to be on October 12th. If you're hearing a rumbling in the background, that is a air conditioning fan or heater fan that I have no control over. So let's try to talk loudly and as clearly as I can. So thank you for putting the time and effort to make sure you understand your homework so you can do well on your test. So without further ado, let's go. Okay, so question one, it says, given that f of x equals the cube root, x cubed, sketch g of x. So x is x minus 3 cubed plus 2. So let's go ahead and write that out right here and do some analysis first. And so the last couple of days we discovered that if we know some basic rules about how these parameters can affect the functions, it pretty much applies to all functions that follow this form. And so we should be able to predict pretty clearly where the graph is going. So the first thing we should probably do is make sure we understand what transformations control what. And so here we're seeing a minus 3 that's modifying the x. If it's modifying the x, it's going to shift left and right. That has a lot to do with the fact that x is our domain. If we're modifying our domain, that means we're modifying our zeros. If we're modifying our zeros, that means we have to be affecting our x-axis. And so the plus 3 is going to affect our 0 by shifting it to the right 3. Remember, it's going to be an opposite shift here, because if we do shift it as x minus 3 value, the 0 is changing from literally 0 with just the x to now 3, because when we put 3 in for this x, that's going to make our 0, or that value 0. Ergo, we're going to shift it to a plus 3 value. Now, separate from that, we're going to have this plus 2. Now, this plus 2 modifies the function itself. Like once we do the cubing, once we pick an x, shift it by 3, and then cube it, now we're going to take the whole thing and modify it by plus 2. So if we're modifying the function value, we're modifying the range, the y value, and therefore we're going to go up 2 because this is going to be a normal transformation. Now what might help to see this is if we first graph the parent function of just f of x equals x cubed. Now to do that, I'm going to pick some good points here. When you sketch a graph, doesn't mean we don't have to be precise. And so for a parent graph, 0 cubed is 0, 1 cubed is 1, 2 cubed is 8, 1, 2, 3, 4, 5, 6, 7, 8, and then we can see a symmetry going the other way. And so this is actually going to be our parent function. This is going to be our f of x equals x cubed. So now if we want to map out our new function, we can think of this as just shifting to the right 3 and up 2, which means we can actually do a point-by-point analysis. So if this point right here was 0, 0, and we're shifting to the right, we're shifting to the right 3 and up 2, we can think of this as a 1, 2, 3 right, up 2, and so our new point should be 3, 2. We can do that actually for all the points, and so if we take the one that was at 1, 1, and we shift it to the right 3, we're going to start at 1 and go right 3, so that's 2, 3, 4, and we had it 1, now we're up 2, 1, 2. Now if you look, the spacing between these 2 points is actually precisely the same. It just happens to be shifted to the right 3 and then up 2. Again, we can see this for this third point we picked. We were at 2, 8, and now we shifted to the right. We should be at 2, 3, 4, 5, and then 8 up 2. Sorry about that. So we shifted to the right 1, 2, 3, and then up 2. And so now we should be at 5, 10. And so we don't have to have a clear sense of, like, you don't have to have you just have to have a clear sense of how it changed. You don't necessarily have to have like a graphing calculator to do this. Now we can also shift this one down here that was at negative 1, 1. It's going to shift the same way. And so we can move this to the right 1, 2, 3, and then up 2. And again, observe the spacing here is exactly identical to what it was before. It's just over to the right and up 2. Now I would also ask you to find the domain and range. So the easiest way to do this, besides looking at your graph, which is always going to be kind of a scary prospect because you're not quite sure if they graphed the original correctly, we can look just at the function. So if we think about f of x equals x cubed, and think about its domain and range, what numbers can you put in for x? Well, it turns out to be everything, so that's going to be negative infinity to infinity. Like there's literally no number that you can't multiply it by itself 3 times. So we can take all the numbers. So using set notation, starting at negative infinity, going to infinity. And in terms of our range, well, if I can cube any number, that number could end up being negative, it could end up being 0, or it could end up being positive. And so the range here was also going to be infinity to infinity. If we look at our new function, g of x equals x minus 3 cubed plus 2, we shifted to the right 3 and then up 2. That means we shifted our x's by 3 and our y's by 2. Now, in this particular case, though, since we started with negative infinity to infinity, if I shift to the left or right just a few values from infinity, that really won't change the fact you're still at infinity. The best analogy I can give you is this. Imagine like a really rich person, like Bill Gates or Oprah Winfrey. If you like steal $3 from them or you give them $3, they're not going to notice it. They're still going to have a ton of money. But if you take someone like really poor, like say like a teacher, and you steal $3 from them, well, they're going to notice that because they don't quite have as much value. And so since we have infinity to infinity, and even though we're shifting our domain by 3, we're not going to see the effect on this function. It's still going to be infinity to infinity. Same thing with our range. Yeah, we're adding 2 to each of our range values, but that's still going to go from negative infinity to infinity. All right? And so you can do a much deeper analysis on these functions if you're able to understand how they shift. So in this particular case, we shifted to the right 3 and up 2, but it had no real effect on our domain and range, just the way our graph looks. So most of the graph is going to remain exactly the same. So here we have a couple questions. So we have this general function t of x listed with parameter changes as variables. So a, absolute value of x plus b plus c. And then we have a very specific t of x, which is for absolute value of x. Why does changing the parameter of a to 1 to 4, because it is 1 here as a default, cause the function to stretch vertically? So if we want to get a sense of what's going on, we can look at the graph. In fact, that's not a bad place to start. So we have like the standard parent function, just the absolute value of x. And then we have this new function, 4 times the absolute value of x. Now, if you just memorize the rule or remember from class, this is going to be a vertical stretch. This question is asking why. The best way to ask a question or answer a question like this is to think about this as a point-by-point analysis. So we have a point here at 0, 0. We have another point here at 1, 1. Let's pick another one here. Let's call it 3, 3. Now remember, this is a parent function. That's where I'm getting this. The absolute value of 3 is 3. The absolute value of 1 is 1. Absolute value is 0, 0. Now, if I want to graph this 4 to the x, just look numerically like what actually happens. This is literally 4 times what you used to have as a value, 4 times the absolute value of x. So if we go to 0, the absolute value of 0 is 0. 4 times 0 will still be 0. So that didn't actually move. That stayed where it was. But if we look at 1, 1, well, if you take the absolute value of 1, the x value, and then multiply it by 4, it should have been here, but now it's literally right here. This becomes 1, 4. So we can already see our function growing much more rapidly. If we go to 3, multiply that by 4, it's going to be way up here, but that's going to be 3, 12. And again, we can see this pattern kind of continuing up here. So we can do that on the negative side as well, but we're going to see a similar effect that is not going to have a significantly higher value. So if you think about if you stretch something like a rubber band, you hold one end, you grab the other, and you pull. So it tends to be like when you make a stretch on something, you have to anchor it in one point, and then you pull the rest up into a direction. So if you look at the function, that's exactly what's happening here. We have this anchoring point at 0. That's not going to move because, well, 0 times anything is going to be 0. But then you're going to take the rest of the values, and you're going to make them significantly farther away. Now, they're going to be farther away in a straight line. But again, if you think about how you stretch something in real life, like this is a mimic of that. So you have this 0 that you're anchoring, you're pulling straight up, you're multiplying by a value, and that's why it's stretching. So you're taking a higher value, a bigger value than it's supposed to be. Just like you take a piece of cloth and stretch a rubber band, you're pulling the pieces farther away than they actually should be. Now this is achieved because you're multiplying. It's a certain times bigger or smaller. This is also why you hear the term scale here. Okay? Like this is called a scale because it's now multiple times larger than it should be. This also explains why if you multiply by a number less than 1, it actually reverts into squish, like a compression. Because if I multiply by a half, I'm actually trying to bring the points closer than what they actually should be back to 0, but again, anchoring at a certain point. Okay? This is also why a stretch typically doesn't change the range, because if you look, the range bottoms out, in this case, at 0. And so if I'm going to try to stretch or compress, I still need that point to anchor. And in this particular case, the anchor doesn't move. Now, that's not always the case, but it's the case for a lot of these functions. All right, let's move on from there. Let's do a little preparing for the future. I want to simplify this expression as much as possible. Now, the key feature that you need to realize or see here is that everything's being multiplied. Whether it's a number to a factor, a binomial, or just numbers, this is all multiplication. Now, I do have addition and subtraction, but since that's all in parentheses, that's going to be trapped in those parentheses, and so we're still multiplying factor by factor here. Now, if these were just numbers like 4 and 12, I can do some canceling. So I can say 4 goes into 12 3 times, so 12 divided by 4 nets me a 3. Now, this is on top, of course, because 12 is bigger than 4, and so the division would end up on top. If I can do that for numbers, I can do that for like factors. So x plus 2 divided by x plus 2 is just going to be 1 each, and since it's multiplying, 1 has no effect on my number, essentially canceling it. Same thing with x minus 6. And so the only things I have left are going to be a 3 and an x plus 4. So the final value here shall be 3 over x plus 4. Now this is just a simplification, so it's okay that you don't have an answer for x. It's not an equality I'm asking you to solve, just to simplify. 3 can't cancel into 4 plus x plus 4 anymore, so we're done with this problem. Okay, so we need to explain whether or not the graph below is continuous, whether it be completely continuous or just partially continuous. For either case, identify the interval of x, for x, for which it is continuous. So if you remember from last time, a nice like common law definition for continuity has to do with whether or not you can draw the whole function left to right without picking up your pencil. So if I come in from the left and I'm drawing and, oh, now I have to stop, pick up my pencil, and continue, that shows a discontinuity. So like right here shows a discontinuity. Okay, so this discontinuity, I'll point out, is just in one little spot, one little break. Now, I could still call this function partially continuous because over like this part of the function and over this part of the function, it's still going to be a continuous line. It just happens to hop apart in just one little spot. And so we can actually map out some intervals which is going to be continuous. Now, assuming this continues on in the left-hand direction forever, that means it's coming in from negative infinity. And so it's coming in from negative infinity, it's traveling all the way to 1, and then it starts again at 1, and then travels all the way, now in this case, to positive infinity. And so that's what my intervals will look like. Now I'm going to use interval notation, and if you recall, interval notation has a couple different things involved. We use a bracket for interval notation to indicate we cannot use a number. And we use a bracket to indicate we can use a number. Okay? And so if we want to write the two intervals, the first interval starts at negative infinity and goes all the way to 1. We can never reach infinity, so we're going to use a rounded bracket. We can't use 1 in this case. Now, if you're wondering why we can't use 1, it has everything to do with that open circle. Remember, open circles mean we cannot use. And then we resume again at 1. And then we go to infinity. Now, again, we can't reach infinity. But in this case, since we have a closed circle, recall that means we can use a value. So we're going to use an open or inclusive bracket. And then to show that these two go with one another, we're going to use a union symbol. And remember, that's just like that little U. That U links the two intervals together. And so what this interval says is it's continuous from negative infinity all the way to 1, and then from 1 all the way to infinity. Here we want to solve the inequality and graph the answer below on the number line provided. I did not provide a number line because I forgot. I'm sorry. But we can only go ahead and draw one in. Like, that's not a big deal. Let's go ahead and draw the number line in. So this number line typically starts at 0, and then we're going to stretch in both directions. To the right is typically going to be our positive direction, and left is going to be our negative direction. Okay, so when you go set up solve this inequality, this goes all the way back to algebra 1. Remember that we're just going to treat this like a regular equation, get x by itself. So of course we're going to add 5 to both sides. So we'll end up with 2x is greater than 12. And then we'll divide by 2 on both sides, leaving us with x is bigger than 6. Now, if we go here to 6, in fact, I'm going to shift my number line just a little bit so you can see more values. I'm going to put 6 right here in the middle. That's 7, 8, 9, 10, 11, 12. And 5, 4, 3, 2, 1. Okay, so we're going to start here at 6. Now what we should note is whether or not we can use 6 as a value. If you look at the sign itself, like that is a strict sign, an exclusive sign, meaning that we cannot use 6. We'll indicate that by using an open circle. We want to pick numbers bigger than 6, which means we're going to shade to the right. Okay. Now if I'm writing this as kind of a domain or range, I would use a bracket here at 6. Instead of a rounded bracket here at 6 instead of a square bracket because I cannot use the numbers. And so like I could also represent this answer in terms of like our normal interval notation by saying we're going to start at 6 and go all the way to infinity. Either one of these two ways to write this is perfectly acceptable. Let's do a little factoring and then we're going to find some zeros. Now good news on both these are quadratics. So quadratics means I can factor hopefully into a set of binomials. I won't have to do anything crazy like the quadratic formula. Here, remember, we're searching for two numbers that multiply to 6. Multiply to 8, and then add to 6. So if I think of my factors of 8, 4 and 2 multiply to make 8. I can also make plus 4 plus 2 equals 6. And so that's my factors, x plus 4 and x plus 2. Now in terms of finding factors, I'm finding the values of x that make these two expressions 0. And so my zeros shall be x equals negative 4, x equals negative 2. Now this washes with what I know about degree. Because I have a degree of 2, that means I have two zeros, and then they're both real. Here we're going to do the same thing, but here we have a number in front of the x squared that's not a 1. But luckily, if I look at all three of my coefficients, those are all divisible by 4, which means I can factor out a common term of 4 before I actually start factoring the quadratic. So if I take a 4 out of the first term, I'm left with just an x squared. Then I'm left with a 6x, because 4 times negative 6 is negative 24, and then 4 times negative 7 is negative 28. So I can set this 4 aside, and I can factor the remaining quadratic. So x and x make my x squared. Looks like 7 and 1 multiply to make a negative 7. And if I make it negative 7, positive 1, I get my negative 6. So my zeros here, and again I should have two zeros, are going to be negative 1 for the first term and then 7 for the second. Alright guys, ACT prep. So for every real number x, which means x can be any number that I choose, the expression square root of x over 5 is an integer. This is a really important piece of information, and we should stop and make sure we can interpret this part correctly first. An integer, if you recall, is any positive or negative whole number. So that means when I take the square root of x and divide it by 5, I get a positive or positive or negative whole number. No decimals, no fractions. So that tells me something really, really important. That means square root of x is an integer too. So whatever square root of x is has to be a positive or a negative whole number. In this case, just a positive. And the reason being, if I want to take a number and divide it and end up with a whole number, I can't start with a fraction. If I take a fraction and divide it, or a decimal and divide it, I'll end up with a fraction or a decimal. If I want to end up with an integer, a positive or negative whole number, that means this has to be an integer as well. And moreover, it's got to be positive. Okay. Now this also tells one other piece of information. The square root of x must be divisible by 0. Okay. And the reason being is because I'm dividing it, I'm sorry, not divisible by 0, divisible by 5. Apologies. Okay, and the reason why it has to be divisible by 5 is because right here in the problem, I'm taking the square root of x, dividing by 5, and ending up with a whole number, which means the square root of x has to be equal to something like 5, because 5 divided by 5 is 1. Has to be equal to like something like 10, because 10 divided by 5 is 2. 15, 20, 25, 30, 35, etc. And so the square root of x has to be one of those things, so when I divide it by 5, I end up with a whole number. And so with those principles, now we can start looking through our choices and see which one will also be an integer. So I'm actually looking for the one which is not going to be a positive or negative whole number. Well, the first one should check out, because if you look, the square root of x divided by 5 is what I know to be an integer. And so if I take an integer and I multiply it by an integer, I should equal an integer. And remember, that's what a square is, a number times itself. So that one's going to be okay. Let's look at the second one, 10 times the square root of x. Well, the square root of x has to be one of these numbers. We already determined that by our analysis. So I multiply an integer times an integer. 10 is 1, so the square root of x, that's an integer too. Let's check out the third one. So square root of x divided by 25. Well, again, square root of x, we already determined, has to be one of these values. And so if any of these values divided by 25 is not a whole number, positive or negative, then that's going to be our answer. It's going to be the non-integer. And since x squared of x can be these two numbers, or this number, or this number, those numbers divided by 29 are a fraction, and so this is not guaranteed to be an integer. If I divide by something like 25 or 50 or something, it will be, but since I have these other choices I could choose, I could end up with something like 5 divided by 25, which is 1 over 5. That's not an integer. So C is going to be our answer. You can check the other two as well, being like an ACT question. As soon as you find the wrong answer, it's over. Like, the question should be finished. Okay. So let's take a look at square root of 48 minus square root of 27. Now, the best way to do this is probably just to bang this out manually, meaning that we just have to simplify these these square root expressions and then try to take subtraction. So recall if we're breaking down a square roots, what we're really doing is dividing the square root into two or more smaller square roots that multiply back to the number under that we started. And so in other words, we're looking for two numbers that multiply to make 48. Hopefully we can square root one of them. 48 can be broken down to square root of 16 times the square root of 3. We can do the same thing with 27. We can break that in square root of 9 times the square root of 3. We can do this, of course, because 9 times 3 is 27. The same way 16 times 3 is 48. Now, square root of 16 is solvable. That's 4. So square root of 3 is not, but that's okay. Square root of 9 is going to be 3. And then square root of 3 shall just remain. And so now if we're taking subtraction, if I have 4 square roots of 3, I take away 3 square roots of 3, that will leave me with 1 square root of 3, or just a square root of 3. So here we have as the answer C, square root of 3. And looking there, it looks like I end up with C for both my answers. Just a last little tidbit, the most common answer on any multiple choice test, especially math, turns out to be C. It's slightly higher as a choice, or slightly more often, taken more often as a choice than anything else. That was quite a long video, guys. I'm sorry for that, but there's a lot to talk about. So that's part 2. Expect part 3 on, Tuesday. All right, thank you.